sequences again?
Last time for homework.
And something called convergence and divergence. Okay, convergence and divergence. And so mostly today we're going to talk about sequences. Hopefully at the end we can get to series a little bit. But today will be mostly on convergence and divergence of sequences. So an infinite sequence converges if after some place in the sequence, all the terms of the sequence become essentially indistinguishable from each other. So you're going along term by term by term, and you come to a place where there's a term that's really indistinguishable from 17 over 8. And then every term after that is indistinguishable. It's so close to 17 over 8 that it's essentially 17 over 8. Okay? That's an example of an infinite sequence that's converging to the value 17 over 8. Okay, another way to talk about this is in terms of the limit. Okay, so remember our sequence. This is our sequence in function form, right? A of I, right? So if our sequence was A sub I, in function form, that's A of I, where I is the counting numbers, right? 1, 2, 3, 4. If you let I get really large, then the limit of the terms is some finite value. So this is a real number, right? A real number. So this is the way the first way is the kind of way we think of convergence, and the second way is a more kind of formal mathematical definition of convergence of a sequence. That the limit of those terms is a particular real number. Okay. If it's not that, anything else happens besides that, then we say the sequence diverges. The sequence diverges. So what are some other possibilities for what happens to a sequence that's not this? That's not converging to a particular value. Yeah.
The terms just get bigger and bigger and bigger.
Bigger. Just as someone was saying, infinity, right? So the terms just get infinitely big or infinitely big negative. Okay, what else could happen? Yeah, so the numbers jump around. They never really get close to any particular one number, and they just keep jumping. Okay? So either of those would be considered a divergent sequence. Okay, so example. So let's do the very first 3 examples of, yeah. You're good? Okay, so this is the very first example we did. So here's the sequence of odd numbers. Sequence of odd numbers. Convergent sequence or divergent sequence? Divergent. This just keeps getting bigger. The terms never like hone in on a particular value. That's another way to think of it. The terms just keep getting bigger and bigger. Okay, this is the next one we did. So we did this, and you guys took some time to figure out this general, the formula for the general term. It was -1 to the I times 2i plus 1 over I plus 1 squared. So what's happening with this one? So as I gets large, the numerator increases what? Linearly, and the denominator increases how? Not exponentially. Exponentially is to the I. That's exponentially. Quadratically, right? Quadratically. So how's the denominator going to increase compared to the numerator? Much bigger, right? When we get to I equals 1 trillion, the denominator will be essentially 1 trillion times greater than the numerator because there's an extra I in there, right? So it's like I squared and the top is I. So what about this? To what value? Converging to? 0. Because you're going to get relative to the numerator, your denominator is going to get super big, right? I times is basically I times as big as the numerator. What about the fact that it alternates negative, positive, negative, positive? Does that change it? Conversion? Yeah, so it's kind of like if you imagine a graph, it's going to be like getting closer to 0, just above and below the x-axis, but still honing in, right? Getting indistinguishable from 0. Really, so the positive ones are going to get indistinguishable from 0, and then the negative ones, every other one's negative, they're going to get indistinguishable from 0. So this converges to 0. And then the last one we did was this one, 2 to the I minus 1 over I. How does the numerator increase? 2 to the I minus 1.
That's exponential.
This is exponential growth. When your independent variable, in this case the index, is in the exponent, that's exponential growth. So we got 2 to the I, essentially, and then we have linear growth in the denominator. What do you think about this?
It's going to diverge.
Yeah.
Because the top's going to get bigger.
Yeah,
a lot
2 to the
faster.
I is just going to get huge compared to I, right? So an exponential function with a base greater than 1 will always dwarf any polynomial term. Even if it was I to the 100 on the bottom, the exponential term will beat it by a mile eventually, okay? So this is going to diverge. It's going to get really big. So, and we're going to do more examples. This was just to get a feel for what these are like, okay? Okay, just questions on the idea of divergence or convergence of a sequence. Okay, so there's 2 common forms we want to learn. The first is what we're going to call a P sequence. P sequence, okay? I have toddlers. I know all about the P sequence. Okay? And this is this form. 1 over I to the P. 1 over I to the P. So, in the denominator, is that exponential growth? I to the P. Or is that like polynomial growth? Yes, polynomial. That's right. It's polynomial, right? So if the base is I, this is like x to the 5th, if you think about functions. X to the 5th, x to the 4th, x to the 100th. So like polynomial, not exponential. All right, so we got 1 over I to the P. And so really we want to ask, for what values of P does I to the P get really, really big? And thus the reciprocal, what we have, gets really small. So if we just focus on the denominator, say we want that for what values of P does I to the P blow up? Because then our sequence will converge to 0. Does it make sense? All right, so let's try some examples here. So practice write out the first 4 terms of each of those sequences. And then just use reasoning to say, is this going to converge or not? Is this going to converge or not? So take some time to do that.
Well, 'cause it's negative power. It's gonna flip it. 1 over 0.2. Yeah, 1 over. So it's gonna.
Okay. All right, so we're not going to go through the terms. I'll just trust that you checked with the person next to you that you can write out the first 4 terms. 1 over I cubed. Does it converge or not? Converges to? 0, because I cubed gets really big, right? If the denominator gets big. What about I to the 1/2? Convergent or not? So the question is, it goes back to this question. When P is 1/2, does I to the 1/2 get really big?
Yes.
That's square root, right? That's square root. Yeah, it
It
does.
still gets just slower.
Yep. It'll get big slower than I cubed does, but it'll get pick any big number, it'll eventually get there, and then pick a bigger one, it'll eventually get there. So we're good on that one. What about I to the -2?
So it's convergent on 0.
Is it convergent on 0?
Yeah.
Yeah. So if that denominator gets really, really, really big, then 1 over will go to 0. Yeah. What about 1 over I to the -2? Because we could rewrite that how? I squared, right? And that clearly will not converge, right? So, for what values of P do we get a really big denominator?
When it's greater than half.
So what about fractions less than 1/2? What about 1/3, 1/4, 1/10? Is it going to get big?
So just a bunch bigger than 0.
What's that?
Does it just have to be bigger than
Yep, so all we need is that p to be greater than 0. Even if p is like 1/100th, 1 over I to the 1/100th, it'll take a really long time. I's will have to get really big, but eventually I to the 100th will get big, and 1 over I to the 1/100th will get small and get indistinguishable from 0. So that's what we're saying. If a sequence converges to 0, we're saying the terms eventually get indistinguishable from 0. So the conclusion here is 1 over I to the p. This is a way to say converges to 0. Arrow 0 as I gets very big. That's what the I arrow infinity means. I gets really big. And here's the key. If p is greater than 0. All right, so that's what we call the p sequence. Questions on that one? All right, next real common one that we want to learn is a geometric sequence. Geometric sequence. A geometric sequence has this form. R to the I. R to the I. What kind of term is this? This is exponential, right? So the terms are growing exponentially. So here we got some different things going on. So we want to figure out for what values of r does r to the I get really small, get really big, maybe stay constant, do something else. Okay? So here's the examples I want you to do here. These will be fast. So you can just, how about just 3? 4 if you need, right? So 3 if it's sufficient to do 3, and if you need 4 or 5 for any particular one to still analyze it, you can do more than 3. So will the sequence converge, and if so, to what value? So these are all geometric sequences with different values of r. Do at least 3 terms for each, and then conclude. Okay, and just a side note, this is a common mistake that students run into. So in addition to talking about your conclusion about all those, I'm going to talk about how is this one, this fourth one, fifth one, the fifth one, this negative 3 to the I different from this negative 3 to the I. Those are different sequences. How? Explain. So talk about that, because this is a trap that students fall into sometimes. How are those different?
First one is convergent, just one parameter space on one, no matter what I is. The second one is like 2 to the I, that's divergent, that's just really, really, really big, really, really fast. The third one is convergent to 0, it produces 1. It's like 3 to the I over 1 to the I, which 1 to the I is going to be very safe. And the last one is the fifth one also converges on 0, just from the negative side. It's actually divergent. Once it's like up, it's getting closer to 0. You can approach it 0. Yeah, so it's a conversion. The last one was like 1 or 15, it was like that. One of the ones that we did last week was like negative possibilities was small. It's so small. Yeah. One like negative 3 to the I. That's divergent.
Okay, let's see what you came up with.
It's divergent, just negative 1 to 1, negative 2.
1 to the I, convergent or divergent? 2?
1. It's 1 forever.
Yeah, so it's certainly these values are indistinguishable from 1 because they all are 1, right? What about 2 to the I?
Divergent is really big.
Big, fast, right? 3/4 to the I. What do you think about that? So to get the net, so think about these. You just think geometric sequences. You think about to get the next term. What do? You take the last term and multiply it by your base, right?
Yeah.
So every term is just going to be 3/4 of the previous term. That's what you should have kind of realized as you were doing this. So if you keep multiplying a number by 3/4 over and over and over again,
It's going to converge on.
just going to get super small. All right, what about -1/5 to the I?
Also,
You're always taking 1/5 of the previous value. Now these are going to go positive, negative, but if they get really small, that doesn't matter, right? Because all the positive ones will get really small to 0, and all the negative ones will get really close to 0. So you should. Are we good so far? Is we got done? All right. What about -3 to the I? Yeah. So kind of like really badly, right? Because it's gonna like half of them are gonna get big positive, and every other one's gonna get big negative. So if like there was a worse kind of divergence, it would be this, right? Like this is the worst kind of divergence you could ever have, right? Because they're like splitting up and getting infinitely apart from each other, but it's still just divergent. Okay. What about -1 to the I? What does this do? What's this sequence? -1, 1, -1, 1.
Never hugs in on anything.
Yeah, right. So you're not getting indistinguishably close to some particular value. You don't average them out and say that it converges to 0 because it's the average of -1 and 1. The numbers each term has to get super, super close and closer to a particular value. That's not happening here. Okay, so, and then how is just our side note, how is the red one I drew here? How's that different from this?
Because it's just 3 to I versus -3.
So what's true about every one of these terms? They're all negative. The exponent comes first, and then the negative comes. So if you intend this, you need to write this. Don't write this, because this is just taking 3 to the I and making all the terms negative. So watch out for that. Okay, so can we put it together here and conclude? So when does the geometric sequence converge to 0? For what values of R does it converge to 0? Less than 1 and greater than -1, right? It's in that between -1 and 1. You have some fraction. If you keep multiplying a fraction, you're just going to keep getting closer to 0. Question? Okay, so what about 1? So when it's 1, it converges, but not to 0, right? Here's just a 1. Yeah, you're right. At 1, it converges, but not to 0, to 1. So that's a special case. And then when does it diverge? Yeah, less than or equal to -1, right? Because -1, it does that flip-flop thing. Or greater than 1. So here's so we can summarize all that. So it goes to 0 when? Between -1 and 1. We're guaranteed that the geometric sequence will converge to 0. Again, here's the key. This is our key here. And then the other case that it converges is when R is 1. It converges to 1. So it's that's kind of a trivial case, right? If R is 1, you just have the sequence of all 1s. It's kind of like, who cares, okay? But the more interesting case here is R between -1 and 1, and those will get small for large values of I. Okay, questions on geometric sequences? Okay, so here's just kind of a tool. This is kind of just a general strategy for analyzing sequences. And the first thing is, look for geometric and p-sequences. Look for the ones we just talked about. And you don't have to reinvent the wheel. You can just apply these conclusions that we made, right? So if you have a geometric sequence and R is equal to 2/5, boom, you just know it converges to 0 because 2/5 is between -1 and 1. You don't have to like reinvent the wheel. Okay, so just apply the properties that we just came up with. Okay, for those. So you're gonna be on the lookout for those. All right. If you don't have those, then oftentimes you're going to use like function limit techniques, like stuff that we learned in Calc 1 or in pre-calculus. So the first of those is properties of rational functions. So what's a rational function? That's one polynomial over another. So you have a numerator function and a denominator function. So I guess it'd be I though. And you can this is those rules where you compare the degrees of the two. If you have polynomials. So remember, if the degree in the numerator is higher than the degree in the denominator, what happens for large I? The degree in the numerator is higher. So it's going to get big, right? The numerator will squash the denominator in size, okay, as I gets really big. If the degree in the numerator and denominator are the same, do you remember what you have? So if n is greater than d, it's going to be divergent, right? Degree of n greater than degree of d. If degree of n is equal to degree of d, do you remember how to find the limit of those rational functions? Do you remember? What's that? You could use L'Hopital's rule, but there's a faster way for this particular case. That'll work, but that might take a long time. Yeah, so when they're the same, what the largest, the leading term of each is going to dominate. So you're left with, for large I, you're just going to be left with the leading term of the numerator over the leading term of the denominator. So for instance, if you had 5x to the 7th minus x cubed plus x over 2x to the 7th plus x to the 4th minus 3. So our degree of the numerator is 7. Our degree of the denominator is also 7. So when x gets really, really big, this stuff just goes away, right? Your leading term will dominate for large x, and we'll essentially have our limit will be that ratio. And then the x to the 7ths go away, and so we're approaching what? 5/2, okay? So this is a good technique for some of these sequences. Is if they're a polynomial over polynomial and the degrees are the same, you can take the ratio of the leading terms. And then what about the degree of the numerator is less than the degree of the denominator? Converges to 0. Again, now the denominator is going to run away with it because it's going to get much bigger than the numerator. And so then you'll be convergent to 0. Okay, L'Hopital's rule says that the limit of a ratio of any functions. So this stuff was only for rational functions, one polynomial over another. L'Hopital's rule says that the limit as x goes to infinity will be the same as the limit of the ratio of their derivatives. So you can take the derivative of the top, the derivative of the bottom, and make a new ratio, and it will have the same limit if your original ratio f over g was one of these indeterminate forms, infinity over infinity or 0 over 0. So in the case that you get infinity over infinity or 0 over 0, you can apply L'Hopital's rule, which says you can find the same limit by taking the ratio of the derivatives of your original thing you're analyzing, and you'll get that's the same limit. Yes, please.
When you're saying the ratio of infinity, did you mean the limits of the
So,
original function?
Yeah. So when you're looking at this, and this just gets really big, and this gets really big, then L'Hopital's rule applies.
Okay,
Right.
cool.
Right. Or if this goes to 0 and this goes to 0.
Gotcha.
Yep. Other questions on that? Okay, so limit techniques for functions, stuff you've seen in the past, calculus and pre-cal. All right, so sometimes you just list out, like we've been doing today. List out the first several terms and use good logic and reasoning. Sometimes this works. You gotta, sometimes you just change the form of it. You use algebra and you change it up. And then deductive reasoning and logic. So there's kind of like there's no one size fits all for these, right? They're all different, and you have to just get some experience recognizing what you're looking at and knowing kind of what to do. It's just practice, okay? So I've got a bunch of practice problems you can work on together here. But I do want to. There's one more thing I want to do before the end. So we'll try to keep this to about 10 minutes. So if you don't need to write out the first three terms, so we've already practiced that a bunch of times, so you can skip that if you don't need to. But the key thing is we're going to analyze each sequence as convergent or divergent. So again, we're on the lookout for P sequences, geometric sequences, things we can do in terms of limit techniques that we can do like for functions. And then beyond that, it's just reasoning, logic, algebra, whatever works, okay? Okay, convergent or divergent, this one? Because? Why? Why does it converge to 0? Okay. Yep. But what do you recognize what it is? P sequence. So yeah, so we want to justify. You need to justify. So write out the reason, right? So it converges to 0. Why? Because it's a P sequence with P equal to 1/2, which is greater than 0. Or over here, this is converges to 0. That's also a P sequence with P greater than 1. It's just written in with a negative exponent, right? Okay, so now these other ones. What about the sine one? Convergent or divergent? Okay. Oh. Fight it out. Is it convergent or divergent? So those who are saying convergent, why? Yeah, go ahead.
As the values get larger, it will approach sine of 1/3.
Yeah, so we can just isolate and look inside the parentheses first for large I. What will that converge? Yes, that will converge to 1/3. Why? Because this is rational function. The degrees are the same, so we can just take the ratio of the leading terms, right? 1/3. So as this thing goes to 1/3, what about sine of this thing? So is that divergent because sine is like this? But what we're taking the sine of is getting really, really close to 1/3. So it's not like we're going to head along the sine curve. We're going to get really close to x equals 1/3 and then see what the sine is. Convergent, yeah. Convergent to sine of 1/3. So we're not doing sine of I where I gets big. We're doing sine of a value that's getting closer and closer to 1/3. So then we're going to get closer and closer to sine of 1/3. Does that make sense? So sine of I, yes, that would diverge. Sine of I would diverge. Okay, and what about this last one? Or no, we got more. What, this one? So again, we can start by looking inside underneath the radical, just isolate that. What's going to happen there? I to the fourth minus phi, 6i cubed plus I plus 2.
Really, really big.
Yeah, we got a larger degree in the numerator than the denominator. So that under the radical is going to get very big, and then square root is just going to slow it down, but it's still going to get really, really big. Right? So it diverges since, we could say, since degree of numerator is greater than degree of the denominator. Okay, how about this one? Pi to the I over 3 to the I. What do we, did everyone see what we have there? We could rewrite that. See how we could rewrite that? Pi thirds to the I. And what's that? What kind of sequence do we have?
Geometric
It's a
sequence.
geometric sequence, right? Geometric sequence.
The R value is greater than 1, so it will eventually diverge.
So then we have that's a geometric sequence with r greater than 1. Pi over 3 is a little bit bigger than 1. So this is divergent. This is a divergent. Diverges since it's geometric with r equal to pi thirds or greater than 1. Okay, well, how this one now has a little bigger denominator. Does that help? So similar. So what does 3 to the I plus 1, how could we rewrite 3 to the I plus 1? What does that mean? 3 to the I plus 1. So when you add 1 to an exponent, what essentially are you doing? Yeah. Yeah, so it's like we have 3 to the I, and then if you add 1 to the exponent, you're multiplying by 3 one more time, right? Because this is how many times you multiply by 3. So we're multiplying by 3 to the I. If you have 3 to the I. If you have 3 to the I plus 1, there's one more 3 multiplied in the list of factors. So we could rewrite this as 3 to the I times 3. It's 3 to the I times one more 3. That's what that means, 3 to the I plus 1. So now, convergent or divergent? Still divergent, because we still have this, it's the same geometric sequence, it's just all the terms are divided by 3. So it's still going to get big, just slower, right? It's going to get big 1/3 as fast. So this is still divergent with the same geometric. So it's geometric with r equal to pi thirds, which is greater than 1. Any questions on any of these? Okay, so we want to talk about last chance questions. Factorials. Okay, so this is 4 factorial. It's not 4. Okay? It means you start with 4 and you multiply down by whole numbers until you get to 1. So it means 4 times 3 times 2 times 1. Okay, by definition, 0 factorial is not 0, it's 1. So this is just a fact you have to know. We could talk about why that's true, but it would take too long. So that's a good office-hours discussion. But just as a fact, 0 factorial is 1, it's not 0. Okay, so write out what 6 factorial is and find the value. Go. What is 6 factorial? Write it out, what it means, and find its value.
700. You get that right?
Yeah.
on the light in the hallway, like the key on the light by the front door. Okay, so you should have said 6 times 5 times 4 times 3 times 2 times 1 equals 720. Factorials always end at 1. They always march down, you're multiplying, and you always end with 3 times 2 times 1, every time. Every time. Okay, so write out what this would be, but do it in a strategic way, right? Don't break your pencil and your hand. So write out enough to represent it and then simplify it. So you can use ... So you establish the pattern, use ... And what do you notice about 28 factorial? 28 factorial has as a factor every single factorial less than it. It has 27 factorial as a factor. It has 26 factorial as a factor. And so it has 25 factorial is embedded in 28 factorial. Do you see that? So given any factorial, every factorial for a value less than is part of that factorial. So that allows you to do what? All this is 1, right? So you have 25 factorial here divided by 24 factorial there is 1, and you're left with? Just 28 times 27 times 26. Okay, so I want you to just write this down. We don't have time to do it, but good exercise for the weekend for practice. Just to get you started, when I is 1, what? Yeah, so when I is 1, you're going to get 2 times 1 minus 1, or 1 factorial, divided by 2 times 1 plus 1. 3 factorial. That's the first term. When I is 2, you're going to get 2 times 2 minus 1 is 3 factorial over 5 factorial. That's for I equals 2, etc. So 5 factorial over 7 factorial. So 2 more tasks here for you to do on your own. For the general term, expand and simplify the general term, see what you get, and then decide if the sequence is convergent or divergent and why.